Hello and welcome to the Sci-AI podcast. This is episode number 9, and today I have a great guest with me. His name is JP Deka. JP comes from India, and he is an assistant professor in one of the prestigious universities in India. He's working on building his skills in the field of data science and machine learning at the moment. He has done his Ph.D. from Indian Institute of Technology, or IIT, in Guwahati. He has worked on the predictability of subsequent waves of the COVID-19 pandemic in India and on the mathematical modeling of the pandemic. JP will also share his views on entropy, space travel, quantum computing, and much, much more. So let's go over and start asking him some really cool questions. What is superposition principle in quantum mechanics and quantum entanglement?
Okay, the superposition principle in quantum mechanics. So, to understand the superposition principle in quantum mechanics, we'll need to understand one of the most important fact about quantum mechanics. Quantum mechanics is said quantum. Why? Because in a quantum system, we cannot have a continuous band of energy. We can only have quantized energy values. Like take the simplest problem in quantum mechanics, which we are taught when we are in college. Like that is the particle in a box. So in this system, the particle in the box, it cannot have any value of energy. It can have only fixed quantum energy levels. So in this particle, so there can be there is a ground state of the system, then there is the first excited state, then there is the second excited, and the higher excited state energy states. So in quantum systems, in this quantum particle in a box, so quantum superposition principle states that the total quantum state of this particle will be a linear superposition of all the independent quantum state of the system. And each of these individual quantum state is attributed to one single energy values. These are all like discrete energy levels. So these are quantized energy levels. So these are all discrete energy levels. So this is what is the quantum superposition principle, which states that it's about the quantum, like in quantum physics, it's called the wave function. So I'll not go into the mathematical details of what is a quantum wave function and all those things. But that is what is the quantum superposition principle. On the other hand, quantum entanglement. Quantum entanglement can be understood by a very simple thought experiment. It has not been done in the lab, but it's a thought experiment. In this thought experiment, one particle is splitted into two different particles. And one of the particle, if you measure and you find like the energy, not the energy, I'll say the angular momentum. The angular momentum is like pointed upwards, then in the other particle, it's going to point downwards. Of course, this is also like from the basics, like the conservation of angular momentum, it states this, like if one is pointing upward, the other is going to point downward. But what was very interesting about quantum entanglement is, if you are measuring the angular momentum of one particle in, for example, the Andromeda galaxy, which is light years away from here, and the angular momentum of the other particle is measured by another observer in the Milky Way galaxy. The solar system is in the Milky Way galaxy, so it's near to us. So these two galaxies are light years away. And quantum entanglement, there's like if its angular momentum is upward in one of the system, the other system is going to point downward. But what was very interesting about this is, like you are measuring in Andromeda galaxy, the other observer in the Milky Way galaxy will tell, I have the exact opposite characteristics in the system. So and this is going to happen instantaneously. Instantaneously means the information from one of the observer in the Andromeda galaxy is transported to the Milky Way galaxy in a fraction of a second. And what was so interesting about this system, this thought experiment, was that it is violating one of the basic postulates of the special theory of relativity. That is, which states like the velocity or the speed of anything cannot exceed the velocity of light, which is 3 into 10 to the power 8. But in this thought experiment, the measurement of angular momentum of the particle in one galaxy light years away from here and the other galaxy in this nearest to our solar system, like the information is transmitted instantaneously. And this is actually violating the special theory of relativity, the basic postulate, like it's like information is being sent at an extremely fast pace. And this was one of the most important and most interesting aspects of this phenomena, which is also known as quantum entanglement. And this quantum entanglement, it facilitates all like why quantum computing is extremely efficient. And in quantum computing, if we can build like this laptop where I'm giving, this is a classical computer, this is not a quantum computer. So if we have a quantum computer tomorrow, we can solve the most complicated problems very easily, because this information from one galaxy light years away to the other galaxy, which is light years away from that, this instantaneous thing, this is also observed in one of in a theoretical aspect in one model of quantum mechanics, which is called quantum walk. So I will be answering about this in other questions. So this is what is quantum entanglement.
Fantastic. That's a great answer. So let me ask you a follow-up on that, because you said that, it is differentiated from the theory of special relativity, based on which, science has established so many laws and theories and mathematics, and so much research has been done since then. So when quantum entanglement, the process that you mentioned, sort of defies it, does it makes scientists differ from each other in terms of, hey, we are going to still work on the special theory of relativity and also some of the science fundamentals based on that, the speed of light, the travel, space travel and all, while there is another faction who totally only works on quantum entanglement and like the process you mentioned, because like you said, it is different and it is yet not been proven in a lab, like you said. So yeah, if you can share.
I will share the special theory of relativity as postulated by Albert Einstein. This theory was in classical systems. These are not quantum systems. Quantum systems, on the other hand, they are entirely different. If you read, for example, Richard Feynman, he wrote this book like this. He has 3 books on the principles of physics. In one of the book, he says, what is the electron? Is it a particle or is it a wave? Then he says that it is neither. It's not. Right. So this the quantum systems, quantum physics, it's entirely different from the classical physics. And special theory of relativity, and then we have general theory of relativity. Scientists are trying to formulate a theory in quantum gravity, and one of the promising theory in quantum gravity is the string theory. The string theory. But the thing is, these theories are still hypotheses. These are not experimentally proven yet. So as long as we are not able to prove this theory, this hypothesis experimentally, we cannot the quantum realm and the classical realm, they are 2 separate realms. They are entirely different. And I think Albert Einstein, or maybe I think Richard Feynman, he said nobody understands quantum mechanics because
Right.
it's like one of the most bizarre theory. It's like the superposition principle, quantum entanglement. Most of the observations that you see in quantum systems, you will not find those in any classical system. In classical system, yeah, you can.
Yeah, I think Richard Feynman said it. You're right, and he said if you understand quantum mechanics, then you do not understand it at all. Uh, so yeah, there goes the paradox. But great explanation of that, JP. If I can just ask one more follow up on that,
Yeah, yeah.
is that how then quantum computing is such a relevant field when nothing in quantum physics, like you said, is been established? There's still hypothesis.
No, 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 not
How are they
no.
then building? Oh,
Not
sorry.
not not
Yeah.
in quantum physics. Many of the quantums, like the theoretical, the hypothesis of quantum physics, they have been experimentally proven. But string
Right.
theory is not experimentally proven yet. Like it's
Right.
still a hypothesis, so that one we can keep it apart. Like, but quantum
Right.
physics is a very successful theory, and it has actually given us many things. Like for
Mm.
example, like NMR spectroscopy, like which like or the MRI, like in the medical sector. These are all based on quantum systems only.
Fantastic. Fantastic. Great. So how, based on these theories of quantum entanglement, like you said, it is still not been proven yet. How are they able to build quantum computers then,
Uh,
like really physical quantum
okay. You
computers?
have actually misunderstood this answer. Quantum entanglement is also an experimentally proven thing. It was actually experimentally proven, and
Okay.
now quantum entanglement is seeing very, very different things. Like now people are finding quantum entanglement in mathematical speaking, like these are continuous systems, like variable quantum entanglement. My PhD supervisor, he's working on this field. So
Right.
quantum entanglement is a experimentally proven fact. String theory is not yet experimentally proven.
Right.
Like
Right.
in string theory, one of the like most important fact, like that's one of the important, like the string theory is like it's quantum gravity, like where you quantize the general theory of relativity. But one of the like this quantum gravity says like the quanta, like the if you take a gravitational wave and you like break it apart, like the minute particle, the quanta, like the photon is the quanta of light. So there is one particle called the graviton, which is hypothesized as the quanta of gravitational waves. Like even gravity, like the gravity field, like quanta of gravity. But
Right.
that has not yet been experimentally found out. Maybe in the future when it is going to be found out, then that will have a very different like experimentally doable things after that.
What is the difference between classic reservoir computing and quantum reservoir computing?
Okay, so to understand what is the difference between classical reservoir computing or quantum reservoir computing, so we need to understand like what is classical computing and what is quantum computing.
Right.
So these are all both like advanced topics, but even before that, we have a very interesting system which is called the classical random walk and the quantum random walk. So what is the random walk? So basically, suppose I give you a coin and you just toss it. So if you get head, you go to the right. If you get left, you go to the you get a tail, then you go to the left. So
Right.
in mathematically, I will say like you have a 50% probability of going to the left or to the right. Now in this system, if I give you a coin and I ask you like you take this coin, you get a head, you go to the left or the right, or you get a tail or you go to the opposite. So
Right.
if I give you such a coin, so you have a classical coin. So like a classical coin is something which you can touch, you can actually hold. This
Correct.
is a classical coin. So if I say then that you take this coin and you take 1,000 steps, after 1,000 steps, if I come back and see where you are located, then if this is a classical random walk, then you are most likely located exactly where you started. This is a classical random walk. So you have an equal probability of going to the left and an equal probability of going to the right. So in such a system, you are going to be found exactly where you started, basically. So this is a classical random walk. But in a quantum random walk, the difference is, so you take, you toss the coin, you say you see it is a head, then you take a step. But after that, you take the step, you are located at one position, but your position is not a deterministic position. Basically, you are not located there. You are located as a quantum superposition of either to the left or to the right. So if you do 1,000 steps in a quantum walk, you are going to be found at the extreme ends, basically at either the extreme left or in the extreme right. You are actually going to be like in an entangled state, either in the extreme left or in the extreme right. So this is like, so what we can see, like in a classical random walk, your position doesn't change. In a in a quantum random walk, your position is going to change. Mm-hmm. So after that, you will have something called the reservoir computing. So I'll have to give a small description about what is reservoir computing.
Sure.
So let's say you want to do some deep learning using neural networks in Python. Mm. So you will use Keras, which is like supported by the TensorFlow library. So Keras, if you use the neural network that it is going to generate is going to be like added sequentially. Like there is going to be a layer 1, then a layer 2, then a layer 3. But in a reservoir computing, all the nodes of your neural network will be located within a reservoir. Basically, like for example, a dam has a reservoir where you collect all the water. Similarly, a reservoir is as a collection of all the nodes of the neural network. So inside the reservoir, if you actually use quantum computing, so I have already said what is like quantum walk is going to give you. A quantum walk is going to give you like you are not going to stay exactly where you started. You will be in the extremes. So what this means, there is like a ballistic transport of information. That is what also happens in quantum entanglement. If the two observers are 1 light year away and they measure at one point, the other observer is going to see the exact opposite. What this means, there is ballistic transport of information. Similarly, within the reservoir, if you don't use a classical random, or not a random walk, basically a classical walk, but you use a quantum walk. A quantum walk is going to support ballistic transport of information. And in any classification model, basically in any binary classification model, like a mammogram data or diabetes data or heart attack, it is either 1 or 0. Like a mammogram, the breast, the tumor that has been observed, it can either be malignant or it can be benign. So what this tells you, that this is exactly what you are seeing. Like it is either binary classification. Even the quantum walk is also a binary classification, either at one extreme or at the other extreme. So if you take all these things in a quantum reservoir computing, I am sure like you will have a classification model that is going to be highly accurate, and then it is going to be extremely fast. And that is what we are looking for in a quantum reservoir computing.
Right. Perfect. Great answer. So that means that quantum reservoir computing is far more advanced than a classic reservoir computing.
Yeah,
Is it?
you will not even believe, like, quantum computing can actually solve the most computationally complex problems. Like in computer science, we have this thing called the n equals to np.
Yeah.
The
Yeah.
NP had like non-polynomial deterministic time. I don't exactly know what these are, but some scientists actually have like worked like on quantum computing that can solve these problems. And if these problems are solvable, then who knows that tomorrow we may have the solution of some of the most computationally complex problem. Like for example, the traveling salesman problem. That is a computationally complex problem, like giving a salesman like the best possible way to deliver all the packages. So that is like quantum computing is a very like promising field of computing.
Fantastic. Okay. Yeah. Why self-driving cars? And writing the best algorithms and model for it is the toughest problem right now. And according to you, then what is the trolley problem and how can it be fixed?
Okay, so let me start with the trolley problem. Then we will be able to understand why self-driving cars are extremely complex.
Right.
So the trolley problem, it states, suppose you are driving a car, not necessarily you, or an AI-driven car. So if the AI is driving that car and the AI within the car, it sees like in front of the car there is one small kid who is likely going to be struck.
Right.
And then the AI needs to take a decision either to avoid that kid who is right down in the middle of the road or to the left or the right. So in the Western countries, we always drive a car on the right hand side. So if that car is going to take a turn towards the right, because that's where the pavement is, where so to avoid that kid. So
Correct.
now this car needs to be taught would think that we have to avoid the kid which is right down in the middle of the road. But the complexity in this problem comes when there are 3, 4, 5, 6 people who are eating an ice cream or just walking on the pavement. So your car is either going to hit that little kid in the middle of the road or the group of people who are down in the pavement drinking a cup of tea, coffee. So how will you teach this car which decision to take? In the middle of the road, you have a little kid, and on the side, you have a few grown-ups who are like doing something. So
Right.
this trolley problem is a very complex problem, and when like these kind of problems will be solvable by the AI built within the car, that day I feel we can start to trust in these AI-driven cars. And the other aspect is right, and the other aspect is to the left. To the left is like there may be a car. So if you are driving a car in Germany, like in the Autobahn, cars have a speed limit. The cars are coming very fast. So if that car has to take a direction to the left, then that car is going to be struck very badly by an incoming vehicle. And that may lead to the death of the driver, his companions who are within the car. So this is the trolley problem. And I feel that the day when we can actually train an AI-driven car to take the most appropriate, the most human decision, that day I feel, now we have successfully implemented AI in cars.
Right. I mean, how will you write an algorithm which sort of covers all the scenarios that are possible, as compared to when a human brain is looking at it and thinking about the different scenarios to avoid nearly 99% of crashes. How would you train such an algorithm? How would you create those models? Can you talk about them as well?
One of the way I think in which we'll be able to train these AI-driven cars is via reinforcement learning. And the reinforcement learning is based on the rewards and reinforcement learning is based on the reward system.
Okay.
So so we need to be able to see which is going to be the most rewarding instance. The people in the pavement, the kid in the middle, or to the left. Basically, your own car being struck by an incoming car and maybe led to the death of all the people who are within the car.
Right.
So that is why the trolley problem is a very complex problem, and it is not yet. I don't know exactly the current status where the AI-driven cars has implemented this aspect, but I feel like we should come across a solution very soon.
Okay. So in a near future, it is possible to solve the trolley problem.
Everything is possible. I am a physicist.
Right.
So you can continue. I will continue speaking about the history of physics then.
Right. No, great discussion. Great answer, JP. So my next question to you is, I was going through your profile and I read an article about butterfly effect that you've written. Really liked what you shared there about the order in chaos. Can you explain this more and why is it so complicated to understand?
Okay, so to understand the butterfly effect, we need to look at a little bit of history. It is a bit of technical history because the guy who came across this phenomena, so he was actually, what he was trying to do, he was actually trying to solve a set of equations. These equations are modeled about the weather effects, like the weather is going to rain tomorrow or it's going to remain dry tomorrow. So this guy, I think it was in the 60s or the 70s. At that time, computers were not that fast. We didn't have a supercomputer also at that moment. So he was actually, this is a bit technical. I have to actually explain this.
Sure.
So this guy was solving the system by taking the system's conditions correct up to the 6th decimal place, basically 0.000 then 001. So this is a highly accurate, basically it's a very big accuracy. And at that time he didn't have any computer to do these problems. So what he did, so I'll not take the conditions correct up to the 6th decimal place. I will take the conditions correct up to the 3rd decimal place only. So he started solving the system again. So for some time he was getting the original solution only again. But after some time he started seeing that the original solution and the new solution, they don't match with each other anymore. So this guy, in one conference, he presented his results in which he showed this is the system I have and I'm trying to solve it with different conditions, but I'm getting very, very different results from moving from 10 to the power minus 6, basically 6th decimal place to the 3rd decimal place, that is 10 to the power minus 3. So then one of the audience member, one of the professor who was sitting in the audience, he said, do you mean to say that the flutter of a butterfly's wings can cause a typhoon halfway across the world?
Right.
So this is where like the flutter of a butterfly's wings, that is where like the butterfly effect terminology came into this field.
Right.
Which today, as I did my PhD in this, and in scientific terms, it is known as chaos theory.
Right.
And if we have to go into the extreme mathematical aspect, then it is said sensitiveness on initial conditions. I'll not go into that. That is a bit very complex.
Right.
So these systems are already complex. These systems don't behave the way a normal system is going to do, because take for example our weather forecast. So tomorrow it's going to be, so I am here in Assam, this is in India. So tomorrow it's going to be around 31 degrees Celsius, or tomorrow it may rain.
Right.
So today the meteorologists, the people who are in like the climate science people, they can give you a very high probability that tomorrow it's going to rain, or tomorrow it's going to remain this hot or this cold. So why these scientists can give you such forecast with such high accuracy? It is because they have data not of yesterday or the month before. They have data for several years, maybe more than a decade, that with using which they can give you a very accurate forecast that tomorrow it's going to rain, tomorrow it's going to be hot, or it's going to be cold. So they have data. So this is where, so when you, like these systems are already complex, I said. So,
Right.
but when you have the data of these systems, from the data, you can see that it's not complex. Things can be predicted, and which is also known as the order in chaos.
Correct.
So this is where like the order in chaos comes. And if I have to go for the very interesting, you can read about fractals. Fractals is basically a very interesting field in like within my PhD research. So fractals is basically, so even like the most complex systems, they can have a certain amount of order within them, and the more data you have within your system, the more accurate you will be in predicting. So this is what is like order in chaos, and what is chaos theory all about.
Fantastic.
And,
Great explanation of that.
And I want to say one thing more about
Sure.
the recent heat wave in Lytton, like in Canada, where people like the heat wave, which actually it's like it made all like it just stayed stationary in one single place. So what this is this thing, like I have never heard that in Canada you can have temperatures more than 30 degrees Celsius. I always have the or like the perception that Canada is a very cold place, so the temperature should be below 20 degrees Celsius. But when I heard like it was 50 degrees Celsius, I was like, what? This is really... So what in like I studied nonlinear dynamics, basically chaos theory. In my field, such a kind of weather pattern in a place where you have never seen something this hot, this is like classified as an extreme event. Basically in data science, it is basically an outlier. So this is an outlier, and like in my field, like in nonlinear dynamics or in chaos theory, this is called an extreme event. Like one of the kind of extreme event which is observable is the rogue waves. Like in a sea, sometimes without any forecasting, you can have enormous waves. That means that they can be very, very huge, and they can actually topple down the most powerful ocean liners even. So these are like extreme events, then this is like a rogue wave. So these are like some unexpected things which is observable in physical systems, in weather-based systems, and even in optical systems as well.
What is entropy? And how does any system go from an ordered state to a disordered state? Why I'm asking you this question, JP, is because I also follow a theoretical physicist, one of the best ones in the world. His name is Mr. Brian Greene, my favorite scientist. He talks about this, in his books, in his podcasts, in his World Science Festival, everywhere, is the fact that one day, not just even all the matter of the universe will cease to exist, but even the very last thought in this universe, even the last thought in the universe will come to an end. So what a mind-blowing thing, it is to know that it can happen. It is just a theory, but still. So can you talk about it a little bit and help us with this question?
So entropy. So entropy, in the simplest terms, basically a school-going student's terms, he is going to be introduced entropy as disorder in the system. Like as a disorder in a system. So what is so special about this entropy? This thing called entropy. So this entropy of any physical system, not only a physical system, of the entire universe, it is going to increase. Why it's going to increase? That is what is postulated by the second law of thermodynamics, that the entropy of the universe will continue to increase. So this is what is entropy. Entropy is basically what we say as disorder within a system. But what is disorder? How can you just a disorder is something which is measurable of quantity. Yeah, you can see it like there is disorder in this system. So to understand entropy even better, this entropy also has another interpretation, which is like the entropy in terms of the probabilities of the state of the probabilities of different state a system can be in, which is also known as the Shannon's entropy, which is also used in data science. Basically, S, which stands for entropy, is equals to K minus KB, then summation over Pi, then ln Pi. This entropy, these are like the two interpretation of entropy. One is like the interpretation of disorder. The other is like this probability-based interpretation. So, what is so interesting about this entropy? If you actually want to know about this entropy, why it's so interesting, I asked you to watch Christopher Nolan's movie Tenet, which was released last year.
Yeah. Yes.
So what I can say is, I already said the second law of thermodynamics states that the entropy of the universe will keep on increasing. So why it is going to keep on increasing? That is what is also actually dictated by something which is called the flow of time. A time doesn't flow in the reverse order. A time is always flowing in in one direction only. That is why also the rate of change of entropy is always going to increase. That means it is going to evolve in one direction only. So in this movie Tenet, what it was shown is, like, if you have a gun, a pistol.
Right.
So if you can reverse entropy, you can also reverse time. And this is where it gets really interesting, that if you can reverse entropy, you can also reverse time. And why this is an achievable thing, it's because the second law of thermodynamics states this. And not only the second law of thermodynamics, even as us human beings, like if you watch this movie Interstellar, in which one space vehicle travels through a wormhole from one part of the universe to another. What is this a wormhole? A wormhole is basically, in the technical terms, it is also known as the Einstein-Rosen bridge. And if we have to go even further beyond that, it is also said to be a combination of a black hole, which always keeps on, which has an infinite gravitational pull, and the white hole. A white hole is a purely theoretical construct. It has not yet been observed. Black holes has been observed because, like, the gravitational wave astronomy experiments, they have substantiated that black holes exist. But white holes, no one knows they exist or not. A white hole is something which does the exact opposite of black hole. So, and for a white hole to exist, it should violate the second law of thermodynamics. That means the entropy should decrease. So I don't exactly remember that. Like, this is a very interesting theoretical physics concept. But that is what is a white hole. A white hole actually violates the second law of thermodynamics. So already Tenet has showed, like, you can reverse entropy and reverse time. So if we can manage, like, a journey through a white hole, we may actually be looking at different parts of the universe, those places where we human beings have never been able to go to.
Right. But why did they introduce the concept of entropy in a movie like this? Because, like you said, it is only possible when you sort of go through a white hole. There was no mention of it. How did in the scene, I remember where, she drops a bullet, but she was trying to show that the bullet is actually going up to the gun, not actually dropping down. So how does that become the reverse of a time? Like, can you explain that a little bit more?
I don't actually remember this scene. I just remember where they were shooting bullets and, like, they were reversing the bullets from, like, the glass where
exactly.
Right.
That
what they were actually doing, they were reversing time. The bullets which were supposed to be struck in, like, in the glass panel, we are actually reversing them and putting them back in your revolver or your pistol. So that is
how that is exactly the question is. So how do they understand to reverse the time, or like you said, reverse entropy?
Yeah, they were actually not reversing. They were not actually aiming to reverse time. They were actually aiming to reverse the entropy. And in the movie, it has already been stated, like, human beings have been able to make bullets out of materials that exhibit the phenomena of the reversal of entropy. So that is where I think, where they were able to actually build, like, bullets out of materials which exhibit the reversal of entropy. So when they were using these bullets, they were actually able to reverse time. Like a bullet which has been shot from the pistol, it can again be inputted back into the pistol.
Yeah, absolutely. I mean, one of the things that Christopher Nolan has done it is, like, I don't know about you, but for me, it's like I have to see it again and again to affirm that, what he's trying to show and what I understand is correct.
Yeah.
I mean, it's such mind-blowing things in Interstellar or Inception or recently in Tenet.
Yeah. Tenet was a very interesting movie because I like these movies because they were actually using physics, and even in Interstellar, they actually used the assistance of this Caltech physicist Kip Thorne. Kip Thorne is one of the most famous physicists he's one of the main team members of the gravitational wave astronomy experiments, which has already validated the existence of black holes. So, so that is why Christopher Nolan's these movies are very interesting, I would say. And even in Interstellar, which also ended with like what I would say, like the last scene in which the top is still rotating, whether this is a dream or this is the real world.
No, that was in Inception.
In Inception.
Inception. But you're right, in Interstellar, like I still see it after so many thousand times that I've seen it. Like I still cannot believe that 47 ticks that you go to the Miller planet and you come back, and because of time dilation, they have only spent like an hour, but on Earth it's like 23 years.
Yeah, basically, let me say, like there is this one physics like phenomena which is called it's the twin paradox. Basically, two twins. One stays behind in Earth. The other twin, he takes a spacecraft and he goes at speed very close to the speed of light.
Right.
And when he comes back to Earth to meet his brother or maybe his sister, then he sees my sister has grown so old. That is what is shown at the end of the movie, in which like the main character is still not a very young man, but he's still young, but his daughter
is 100 years old.
Actually, I love that actress a lot, Ellen Burstyn.
Right, yes. Yeah, and it is fantastic. Like, I think he doesn't make Hollywood movies. He sort of makes these physics movies and then put stories inside them.
Exactly.
For me. I think it is like that,
Even in Interstellar, like when they were traveling through the wormhole, like there was one point in which the spacecraft is traveling, but that scene, when I watched the first time, I was like, wow, this is I was like,
this is just unbelievable, right?
Yeah, because
they think about it.
Yeah, because I have also like this one thing in physics, like if you are like sitting right next to a black hole, the light which is like exiting from the back of your head, it's going to take a round trip across the black hole and comes right in front of you. Basically, you are going to be able to see what's right in your head.
Okay. Fascinating. Just amazing concept of black holes. If you're so passionate about it, why not ask you about singularity then? What is singularity in black holes?
A black hole is a singularity. What it is like, see, we have our sun. Our sun is not that huge, but those suns, those stars, which are very, very huge, at one point of time, that star is going to have such a huge gravitational field. It means it's going to attract gravitational force. What it does, it attracts. And that star is not going to have any kind of fuel, basically no nuclear fusion, no nuclear processes is going inside. So there is no outward force, only inward force. So if such a star is a huge star, then all the mass of that star can be actually compressed to a single point, which is a black hole. That means it is basically a star with infinite density. It's like the mass density. It's infinite. That is what is a black hole. So what is this black hole? So the star is located somewhere. So where it is located, that is where like the concept of space-time comes into effect. So that space, so that when it becomes an infinite density, when it becomes a black hole, that is where that black hole is basically a singularity in the space-time.
Okay. So what are then supermassive black holes? Like, why some black holes? Is it because some stars are small and some stars are big, and that's why you have the black holes, or you have the supermassive black holes.
Yeah, the supermassive black holes are basically like the black hole. Basically, they are stars. A certain portion of this star has become turned into a black hole, but the rest, they are still emanating light. Like in Interstellar, towards the end of the movie, what you see, that is a supermassive black hole. Basically, there is a black hole at the center, but those mass, basically those particles within the star which couldn't be into the black hole, that becomes like a bright kind of object which is going to circulate around the black hole.
Right.
Quantum mechanical phenomena. This happens only in quantum mechanics. So this is called Hawking radiation. It was actually postulated by Stephen Hawking. So he actually said like a black hole doesn't always just absorbs or it attracts. It can also emit particles, emit basically photons, which is basically what is Hawking radiation. But I don't know if Hawking radiation has yet been observed experimentally or not, because as long as something is not observed experimentally, we cannot say for sure whether this exists or not.
So it's still a hypothesis, the Hawking radiation is.
Yeah, I think it's still a hypothesis because I haven't heard about the observation of Hawking radiation.
Okay, great. So according to the general theory of relativity, I mean, every place or every instance has a frame of reference, right? So if I am looking at a moving comet or at an asteroid, it is going at a certain speed, and then its time is different from my time. The reason being the difference between the frame of references. Can you say that? Can you say something about that?
Okay, to understand the frame of reference, you will have to understand. Like, let me start it from the very basics. Like,
sure.
We are here in Earth, and the moon is revolving us. And we have seasons, basically summer, then fall, then winter, then spring, because the Earth is also rotating around the sun. So what this says, like, we are not stationary. If you really want to be stationary, that means I just hold you and I just put you somewhere, and you are say stationary, like the absolute stationarity. Then do you know what will happen? You will actually be dizzy, because if you are extremely stationary, you are absolute stationarity. If you are stationary, then you will see the entire universe is rotating. Everything, the stars, everything in this world will revolve around you.
Right. This is an amazing concept. So can you say again for our listeners one more time? If I am absolute stationary, like if I'm not, are you saying if I'm not in Earth's atmosphere, if I'm out of Earth's atmosphere and I'm in the space vacuum?
No.
Sorry.
It's not Earth. It's not even within the solar system. Not even within the Milky Way galaxy.
Oh, okay.
You will have to be somewhere where gravitational force doesn't have any effect on you. Like the absolute stationary is not possible in the realistic sense.
Sure.
Because we are actually otherwise we'll become dizzy and will actually collapse.
Why is that? Is that because space is expanding and then everything in the space, is a matter, and we are also matter, and nobody can be stationary, and that's the reason why? Or why do you say that there cannot be an absolute stationary item?
Okay, absolute stationary is not possible because let me just give you the
Sure.
simplest example. Like we are in the Milky Way galaxy.
Sure.
Even this Milky Way galaxy is moving towards something called the Great Attractor. It's actually moving. The Milky Way galaxy is also not stationary. And if you have to be absolutely stationary, you should not be affected by the gravitational pull from any galaxy, from any stars, from any cosmological body. So that is why absolute stationary is not possible in this universe. And I believe our not psychology, basically with what's within the brain, like it's been designed in such a way that it cannot
stationary.
I attended this one public lecture in which one of the audience member he asked, like, can we be absolutely stationary? Then the person who was giving that talk, he said all these things which I am saying here today.
Okay, great. No problem. Yeah. Okay. Thanks, JP. Next question then. So, as Michio Kaku, one of the famous theoretical physicists, says that we should combine with artificial intelligence in the future because we cannot compete with its intelligence and anything else that it possesses. Why not merge with it? Right? So in the future, why compete with it? We are part cybernetic already when we have our smartphones with us, who tracks us, who knows what our interest is. And, without this, we cannot survive, at least most of the population of the earth. So what is your opinion on merging with AI in the future?
Yeah, merging with AI. So I feel the day is not far when we will be actually merged with AI, because Elon Musk's his own company, Neuralink, where within the brain you can actually control your brain, like your emotions and everything. So everything within the brain, you can actually teach mini robots. Like nanotechnology is also advancing very fast. Tomorrow, tomorrow there may also be a day when a person suffering from cancer in any part of his body, he may be infused with nanorobots that can actually remove the cancerous tissues within the body without the need for any surgery.
Right.
So these are like what nanorobots?
Mind-blowing things. Yeah.
So those are again AI. They are again be driven by AI. So they are basically like doctors, which will be told how, doctors will be training those robots on how to treat that patient with that tumor. And last year there was a game released. It's called Cyberpunk 2077. So in that game, it is shown the day is not far in which the entire human body, basically even our organs, our consciousness, that's going to be what's human. Other than that, we'll have organs which will be basically electronic components, basically what is Bionics attempt to do. Biotech and electronics together within the human body.
I've heard about synthetic biology, wherein they're creating artificial organs in the lab. But what is bionics? Can you talk about it a little bit more?
Bionics. So let's say, for example, our eye. There are people who suffer from diseases and their eye needs to be removed, or they may go blind. So today we have eye donors whose eye we can take and we can restore our vision. So this taking someone else's eyes or taking someone else's organs, instead of this, can we not have things which we can create in the lab, we already have 3D printers today. And I have just heard like people in Japan, they can also make food using 3D printers. So
Wow.
yeah, they were actually able to make food using 3D printers. So, and like in IIT Guwahati, there was this one professor who was researching in in creating artificial pancreas. Pancreas is the organ which if we don't have, we'll all be suffering from diabetes or high blood sugar. So this professor was I think he's still working on this topic on artificial organs for the human body.
Wow. Okay, great answer. What is your opinion on how we can ever be able to travel beyond our solar system or our galaxy? What kind of spacecrafts which can travel near the speed of light would be needed so we can reach the distant galaxies in the matter of some months, because otherwise it's pointless going with the speed of the spacecrafts that we travel today.
Okay. For that, I will have to actually tell you this universe is not like the distance between my home city or Delhi, like where you can take a flight and reach there just in 3 hours or 4 hours. The universe is huge. If we have to actually travel beyond our solar system, the first thing we will be needing is how we can preserve ourselves. How we can put our body in such a system that will prevent us from aging. That is the first important thing. The speed of the spacecraft, that is the other aspect. Because once you go outside the gravitational pull of the Earth or even the Sun, your spacecraft is not going to it's not going to come across any kind of force which is going to be like a damping force. Basically, it's going to give some retardation to the acceleration of the spacecraft. So the most important thing here is the preservation of the human bodies to stop us from aging. Once like I have I think 1 or 2 years ago, scientists in London or like somewhere in England, they were able to build the first artificial womb. Like today, the human baby doesn't need to be taken care of inside the mother's uterus. The human baby could also be taken care in an artificial system. Scientists have already done that. So who knows that in a few years we will have scientists who will be able to preserve the human body, prevent it from aging, so that once we identify what is known as the Goldilocks planet, like our Earth is a Goldilocks planet. It is located at the perfect place between not far away from the sun or not very near to the sun. So it's not hot, extreme hot like Mercury is, or it's not extremely cold like Neptune or Pluto is. So that is why when we find such a planet, and if tomorrow the human race has to actually leave this planet, so these are very fields of research which is going to be very, very it's a promising field of research, and it's also the futuristic aspect, because every planet, every system in this world, they have their own time scale till what we can exist in this planet or in this place.
True.
Everything is changing. Like I come from a place which is called the Brahmaputra Valley. And the Brahmaputra, it's one of the rivers of India, and it's a very ferocious river, because the floods it creates in this region is like, it's unbelievable. It's like, I have seen, long back when I was coming from my grandparents' home, via train, I was actually seeing people whose entire homes have been submerged by floodwater. So,
Right.
so who knows that this flood can actually, it can erase this entire valley at one point of time. So that
Sure.
is
Right, absolutely. We have a finite time on this planet. You're absolutely right. What kind of future technologies will be devised, as per your opinion, that can take us to the near to the speed of light? Something like fusion-propelled engines, or warp drives, or whatever. What kind of things will take us to the far galaxies?
in to travel a very huge distance within the shortest time. I feel a warp drive is a more promising field, because a warp drive is what it compresses, like it's also based on what a black hole is, compression and expansion of space-time. So,
Right.
and if we can actually today we have already been able to detect gravitational waves. Who knows, tomorrow we may be able to engineer our own black holes.
Wow. Okay. To propel these engines with super energy and unending fuel of
Exactly.
energy. Mind-blowing stuff. Yeah. Okay. Do you think that we are alone in the universe? Is it possible that such complexity of life like ours be ever present anywhere else in the universe? Sure, there are trillions of stars in the observable universe, and with each star, there must be a planetary system, as we know, and planets in the Goldilocks zones, like you said. Earth is in that zone to become a habitable planet. But still, the way life has evolved here in the universe, is it possible that life may have propagated anywhere else as well? Like, because it is so complex to develop such a life somewhere else with the right kind of ingredients, the right kind of situation. So yeah, what is your opinion?
So life. So in the simplest terms, like the life which emerged in this planet, that happened like billions of years ago. And human beings have been here in this planet just for, I think, 5 minutes or less than 1 minute. Because so life, so like, let me tell you one research about the history of life. So there was this two research professors. I don't remember where they are from. They are known as Miller and Urey. So Miller and Urey, they did one experiment. So what they did is they took a dish of water, and there they put some of the earliest elements that were present in art. And they started, like, after that, they started zapping those elements in that water dish with electric shocks. After some time, they take back the dish and they analyze it. What are here? And they found like this contains amino acids. Amino acids is the building block of the DNA. It's a building block. So they found amino acids. So from there, they gave the hypothesis, like thousands, billions of years ago, the amino acids in the prebiotic pond, like life didn't exist till then. Those amino acids, they started interacting with each other. And those interactions at one point of time gave rise to the first unicellular organism, a single-celled organism.
Right.
And from that single-celled organism, today we have that cell has evolved to what is like we human beings, on all the living beings that we see across in this world.
Are we alone in the universe? Life such as ours, with the right kind of ingredients, like you said, with the kind of accident happened because of the amino acids and the microbes underwater, can that sort of thing happen somewhere else as well? Or are we just overthinking and, yeah, it is possible everywhere else, like it has happened on our planet?
Yeah, that their life on other planets basically, see, like the Earth is in the Goldilocks zone. Like it's the perfect place for life to emerge. So there is not just one single solar system which can
Of course, yeah.
which can support the evolution of life from a unicellular organism to a complex multicellular organism. So
Right.
so there is it would be wrong to say that life doesn't exist outside of Earth. Who knows, life may have existed in our nearest planet, the Mars, or maybe some other planet, because we have been here for a very small period of time. There, you cannot just blatantly just say life exists only on Earth.
That's fantastic. That's a great theory. Yeah. Okay. So we are flip-flopping a little bit from these philosophical questions to, again, AI. So let me ask you one more AI question. As per you, who is more dangerous to our civilization? Is it the artificial intelligence that we are building right now? Or is it the humans itself? We have seen with so many lunatics, that have been wrongly came to power, tried to, did genocides and a lot of stuff in the world, and almost trying to nuke, our civilization out. So, yeah, who do you think is more dangerous?
AI will be dangerous if it is a sentient AI. Like we feel love, we feel hatred, we feel so many different kinds of emotions. But how are we going to quantify these emotions so that we can train an AI? So that training that AI and training it such that it is not going to start a civil war against us human beings, because that has already been shown in the movie The Animatrix. Like a civil war between artificial intelligence and human beings. So
correct.
So that is and one more thing is training an AI, there should always be a limit to how much we want to train this AI. When you put a limit to the training of an AI, then I feel the AI can be made to serve us rather than us being made to serve them. So we'll have every single step in the generation, basically in the generation and in manufacturing of sentient AI, it's a very important topic that researchers must take into account before they take the next step.
Right. It's a fantastic point. Yes, absolutely. Okay. What is the meaning of life and why are we here in this universe? Or there is no meaning at all and it is just pointless. We just exist because we just exist.
So you are just meaning to bring out the nihilist within me. Like in Ph.D, I used to read many books of Nietzsche, so I appreciate his philosophies.
Okay.
So life,
Yes.
Life is the equilibrium. The human beings, our life, it's an equilibrium. All the cells within the body, they are in such an equilibrium. They're interacting with each other. They are fueling the life within me. And the other aspect of life is that when this equilibrium, when this kind of this complex processes which are going inside our body, that goes down into a complete disorder, or the entropy keeps increasing, and we reach a point of time when the cells in this human body can no longer support life within.
So does aging means entropy happens to our body as well?
Yeah, if you actually see, like, entropy is what? A disorder which is increasing. Like our body also, we have cells. Our cells are also dividing, cells are also generating at every point of time. Like I watched this one video in which said that every week you are a new you, because all the cells in your body have regenerated for a new you. So
right.
So this generation, so at one point of time, a disorder like where it can no longer repeat this process as efficiently as it did in our younger age. So when this efficiency is going to go down and down, at one point of time it breaks. Sometimes it happens beforehand, which leads to cancer, and a lot of time it happens when we are very old and the cells in our body can no longer support the complex processes that are going inside.
Right. You know, why do we age? Why did evolution chose us to just survive for 50, 60, 70, maximum 100 years, right? Why did that happen? Why was it not 500 years or 1,000 years, or maybe just 10 years, or maybe 10 days, like some flies or, some other organisms have such a short life. So yeah. But I had so much fun, listening to what you said, JP. You have really surprised me with some of the topics like Hawking radiation, others that you've talked about. And I'm pretty sure, like myself, lots of people who will watch this video and this podcast will definitely benefit from it.
And
thank you so much for answering these questions.
And thanks a lot for inviting me also, because I also like to talk about these topics. I actually enjoyed all those questions which you gave me. Like when I used to sleep, those questions, like they keep revolving around in my head.
Right.
So like they give the perfect answer.
Right. Yeah.
Yeah, that's
we
all.
don't need the perfect answer. We just need your answer. Exactly. Yeah. Right. Perfect. Thank you so much. It was a pleasure to have you on the podcast, JP. You have a good day. Take care. Thank you for listening to this podcast. Please support this podcast by liking, commenting, sharing it with your friends, and also subscribing to this channel. Thank you, and we'll see you next time.